So welcome everybody to the 12th and last lecture from my side for the discourse on robot learning. Before I start with today's topic on the frontier and open problems, I did make a slide, but just a quick announcement for the projects. We will send you an email tonight with some information for the PCs where you will be able to test your policies. We basically we found a bunch of PCs at my work at Microsoft, and we brought them to ETH. We put them in a room, and this will be the PCs that you will also deploy your policies on in demo day. And so we will give you information on how you can access them, I think starting tomorrow, like later tonight via email. Yeah, that was a kind of a quick announcement before we dive deep into today's topic, which is, I'm going to talk today a little bit about frontier and open problems in robot learning, and then I will end a little bit with some tips also that I found helpful on how to do research, for example, like if you're interested in tackling any of these problems. So to begin with, let's start with something you've probably seen if you follow robotics on social media. Because pretty much every single week someone declares that robotics is solved or manipulation is solved. Yeah, so I don't know, a few days ago, Genesis AI dropped a new announcement, and they declared we're approaching the end game for robotics. Brett Adcock also tweeted about having their ChatGPT moment for robotics in their lab. 2 years ago. We're still waiting on that. And others promised like the roadmap to physical AGI and so forth. And so I'm not saying, this is not like criticizing, or I'm not saying you shouldn't believe this announcement or anything, but just take them, you might want to take them with a grain of salt, because essentially, how can you believe them is somebody else already declared to have solved robotics the week before, right? So what happens when you ask to a robot to actually generalize, right? And so on the left, you can see the Boston Dynamics humanoid, and on the right, a mobile manipulator from Stanford trying to perform cooking-related tasks in a kitchen environment. And as you can see, for the kitchen one, you might will have to wait quite a long time until the robot can cook dinner for you. Now, these two videos are not absolutely the latest results. They're a few years old, but they're kind of representative of something important, which is when you take the robot out of the lab and out of the lab setting and put it in a new environment and ask it to generalize, then maybe with the new lighting, new objects, new camera viewpoints, and so forth, things start to break very quickly. And so, although looking at the very impressive and very cool demo videos on social media, you might be inclined to believe that robotics is solved. If you take the same robot on the same demo and put it in the next room, outside its training distribution, it will probably fail quite badly. So how do these cool Twitter demos that supposedly are the ChatGPT moment for robotics or the end game work, or how do they get made? So I want to share with you the really not so secret recipe on how you can do a rockstar demo on real robots. So first of all, just collect training data on your own. Don't rely on anybody else to do so. Just collect as much training data as possible on your target platform. The second step is train a behavior cloning policy, and just keep collecting data until extrapolation becomes interpolation for your policy. And then the third, if possible, try to train and test on the same day to avoid any distributional shifts whatsoever in the environment, no changes in the lighting, no changes in camera viewpoints, table heights, and nothing, right? And so it turns out you can get a lot of money from VCs for following this very simple recipe. But what is the actual problem we're trying to solve in robotics? And I like to think about generalization as this kind of like hierarchy of scopes where like the most impressive demos you see are operating in this very narrow kind of like between one object and one room kind of circle. And of course, like like there's more ambitious work trying to pull towards like maybe like generalizing the one building kind of environment. But the real goal is like the world, right? And because humans generalize to the real world, and you don't need to have seen like every kitchen to cook in order to cook in a new kitchen, right? You don't need to have picked up every possible like object or every possible mug in the world to understand how you need to grasp like a new unseen mug, right? And so basically, like you kind of stitch together your knowledge, reason about novel situations, and compose what you already know in novel ways to be able to do this sort of generalization. And that's not interpolation, right? Like it's really like kind of this this missing like intelligent reasoning or whatever you want to call it thing that is still very elusive for our robot policies. Like we are not there yet. And so this really goes a little bit beyond just collecting more data in order to achieve these abilities, right? And so where we are today is that we have kind of like powerful generalist models, often in the form of like VLMs, for example, that are trained on internet scale data and generalized broadly, but often lack this physical grounding. So they can kind of describe, for example, an image with a glass on the table, but they don't truly understand what will happen if if they push this off the edge and it breaks apart, right? This kind of also applies to generative video models, where I don't know, like models like Sora can synthesize really very realistic-looking, like kind of physical interactions, right? Like liquids pouring or objects falling. But if you look closely, they do actually tend to violate like physical basic physics. So they are very good at making it look like they like the world, but don't really like fully understand like physics, for example. And so, on the other hand, like we do have like specialist kind of embodied models or policies that can perform like dexterous tasks and consume like more heterogeneous sensing modalities in order to better interact in the world, but do tend to not generalize kind of to broader in the wild tasks. And so our quest in robot learning is kind of like to to kind of find like the best of the both worlds, right? And so what is the path forward? I believe that in order to achieve like this sort of like true embodied intelligence, we need to move kind of to beyond like this passive data that like foundation models are trained on towards grounding them in the physical world by feeding them like richer embodied data that is inherently multimodal, spatial, and also temporal. And so ideally, this would then help us build agents that can not like describe the world, but actually reason and like more intelligently interact with it. So this brings us to the kind of first open problem. What is the best backbone for robotics, right? And it seems we have this kind of three camps in the community right now. The first one says like, oh, let's use a vision language model because VLMs already come with all this like rich semantic knowledge about the world. And they can reason about scenes and so forth. So we can fine-tune them on some robot data. And then you get like this, let's say, object level semantic generalization for free. The second camp says, let's use a generative video model because they better understand temporal dynamics. They kind of better model how the environment or the world evolves across time. Their pre-training is a little bit more similar to what a robot policy needs to do, like essentially like reasoning over consequences of the actions, right? And then there is maybe the third camp that maybe is a little bit more provocative that says like, well, the backbone actually doesn't matter that much. If we have enough real-world robot data, then we can just train everything from scratch. And forget about internet pre-training. Like, we just care about robotics. Let's just like collect robot data, train a big model on it. That's it. Well, interestingly, Scott Reed gave a kind of like a guest lecture on exactly this topic a few weeks ago. So if you missed it, it's on YouTube. You can find it on the course website, and invite you to watch it if you're interested in this. And so, yeah, I think in general, like each of these positions has like serious proponents, but the jury is kind of still out on which one is the best way to move forward. And this is closely related, the backbone question is very closely related also to the data question, right? What is the best data recipe for robotics or for training like kind of like more generalist robot policy, right? So there are like different approaches, like for example, on the left, this could be like this three-tier approach where you start with web data, to have like kind of good world knowledge and grounding, language grounding, and then you scale with some like simulated interaction for a kind of like scalable, cheap like experience, and then like kind of a little real world robot data on top to kind of bridge the sim to real gap. The second proponent could be like stripping down the simulation layer. Because, well, the argument these camp makes is that, well, you know, like simulating the entire world accurately is very, very challenging. It needs a lot of engineering, and you might rather better invest the time actually collecting real-world data instead of trying to figure how to simulate all the physics and everything, right? And here are a few more data recipes that follow some of the background choices we just discussed. So on the left, this would be like a kind of like a data recipe that treats video as a first-class citizen, where you kind of start training maybe on general, like YouTube-like internet videos, then add some human egocentric videos for mid-training, and then end post-training it to predict robot actions. The intuition, as aforementioned, is that video is a far richer prior for embodied tasks than, let's say, visual question answering tasks could ever be. And then on the right, you can see like kind of the from scratch recipe of just training like all the layers like with real world data. Maybe like it varies a bit, maybe with on the type of annotations and granularity, but just like really going all in on the real world data. So once you've decided on your data recipe, you also face kind of the next question of like, how do you actually collect like, real world data, right, at scale? Because all of the, like, no matter what, like in the end, like you will need some, like more or less like real world data. And so what you're looking at here is kind of like a zoo of data collection interfaces, each making different trade-offs between scalability, alignment with the target embodiment, and the complexity of the tasks that you can demonstrate. So, for example, Oier Mees style grippers, as you saw in the talk from Cheng, are more scalable than teleoperation robots, but now you need to do like some sort of cross-embodiment learning. Puppeteering gives you higher quality data than VR teleop, for example, but it's the most expensive one. to collect, as you need also like a leader-follower ARM setups, and this means you now also have more hardware to break. And on this plot, you can see a little bit the trade-offs between the data scalability and the hardware alignment. So on the vertical, on the y-axis, you can see how much data you can collect, ranging from thousands to tens of millions of hours. And on the horizontal axis, you can see how closely this data aligns with the actual hardware that you want to deploy on. And so egocentric videos gives you tens of millions of hours of data, but it's human data, it's not robot data, so there is quite a big embodiment gap. While teleop gives you perfectly aligned data with the robot fully in the loop, but you are kind of a bit more capped in terms of like the data volume because it's like slower and expensive, and data wearables, like let's say, for example, gloves, sit somewhere in the middle. So yeah, basically solving these trade-offs or finding like your ways around it, like for example, I don't know, like by having a humanoid robot to better like leverage like egocentric videos or things like that, is one of the open problems that the community is looking at. So what is kind of like the goal we are working towards? And in general, I think maybe one good framing is that ideally we would like to have like dexterous generalist policies. And the challenge is that so far, dexterity and generalization have required somewhat different ingredients for success. So this means, if you think about it, like for example, for dexterity, you typically need high-frequency control. But this is like a little bit at odds with running very large foundation models, right? Because they're like more slow and computationally more expensive. For dexterity, you also typically need more heterogeneous sensing, for example, like touch sensing, modalities that most foundation models simply don't consume today. And on the other hand, if you care about pushing generalization, then you need to leverage foundation models, right? And also for robotics, you also need to think about mobility because robots that can move across different environments and accumulate experience across different like rooms and buildings and so on, they can learn to generalize better than the same robots if they are just like bolted onto a table and like not moving a lot and just like kind of seeing the same scene, right? So the goal is kind of like we want to be like at the intersection of this Venn diagram, where we want to have like systems that are dexterous, but and can handle like kind of the complexities of all the real manipulation tasks, but that are general enough to do so across unstructured environments and like any kind of like unseen objects that we throw at them. And so, yeah, most systems are kind of like in one of two camps, but like that's one of the open problems to try to develop algorithms and systems that kind of go more towards this goal of having like dexterous generalist policies that generalize. So let me maybe illustrate a point about dexterity requiring more than vision with kind of like a personal video from my PhD. Oh, I think you don't. Can you hear the sound? Oh, sorry, I didn't check. Okay, so you can't hear the sound, but what is happening here is, so I spent quite a lot of time training like a model that would take like an RGB image as an input and predict 3D shapes and objects pose, so that even though like a robot, the robot had like a depth camera, because they were like partially occluded. You could kind of predict like the object, like for example the handle of the mark and so on, like very accurately to better grasp it. And what you see here is that the robot like misses the handle, just goes for grasping the mark directly and absolutely destroys it, because it has no touch or force feedback. So it was kind of like doing a blind grasp that was like too powerful. And I think that our current VLAs are also probably still annihilating objects, because we haven't made that much progress in this front. I think our robots are still kind of blind most of the time when we are making contact with objects. And so your first idea could be, well, if you remember, we covered like natively in multimodal models earlier in the course. The idea being that instead of bolting like additional modalities to like vision, we could like try a unified transformer that can from scratch across all modalities jointly, right? So we could throw in like touch, force, proprioception, all of this into it, and we solve the problem, right? But the issue is that the moment you try to do that, you basically run into like what I would call the long tail of robot sensing. And there are like a few issues with this. And the first and foremost, as you probably can guess, is the data scarcity. So many of the modalities that matter for dexterity, like touch, tactile, feedback, force, are usually not available at scale. Because the hardware is expensive, it's fragile, and also like not very standardized. So it's still kind of very researchy. And the second, pairing. So even when individual modalities exist, for example, cross-modal paired data, where you have like all the modalities you wish kind of paired at the same time, that is nearly non-existent. And thirdly, heterogeneity. So sensors vary a lot across different robot embodiments, which makes also transfer quite hard. And given the scarcity of this paired multimodal data, there's also like an interesting question. For example, can we use language as a bridge to reason across modalities that we haven't seen before together? Because we have like kind of disjoint amounts of data, right? Like, for example, we might have large amounts of vision, language data, some audio data, and maybe like small data of touch. But no data to train all of this like simultaneously, right, at scale. So here's some initial work we did at Berkeley on how you can give VLAs senses they were never trained on, like touch or audio, by using language as a semantic kind of glue to bridge all, to bind all these heterogeneous modalities. So I won't go into the details, but basically this unlocks like VLA's new cross-modal reasoning abilities, such as, for example, asking to grasp the object that feels like a pineapple but is brown, for example. And so here you can see like a few different things that then this enables you to do, like multimodal prompting, cross-modal, like audiovisual prompting, or even generation of object descriptions upon interaction. So, for example, in this case here, this is like kind of the scenario where the robot like grasps into a shopping bag and it can't see anything with the camera, and it grasps like a random object, and with based on like the touch sensor, then like describes what it thinks it's feeling. So similar to what a human could do, right? This slide connects directly with what we covered last week on reasoning with LLMs and VLAs. And I want to like kind of maybe touch upon briefly on maybe like a broader question for you guys on like when and how should a robot actually reason, right? So Because now if you think about, okay, like your future robot butler that is like, assisting you at home, reasoning will probably be on like a spectrum depending on like your policy's confidence, right? So when the task you're tasking your robot is in distribution, right? So maybe it's like a known object, a known task, it already has done before, it's like it has training data for this. Then we probably don't want to reason, right? We just like want to run our policy at the highest frequency as possible because, well, we don't want to like waste computation. But then when you detect that your policy is not completely sure about what to do, because maybe it's like a new object or maybe the lighting is different or something, that's where test time compute, adaptive test time compute becomes valuable, right? And basically with like some of the techniques we saw last week, we can try to think through like the task at hand by spending more tokens on it at test time to solve it, right? And then on the third column, this is like the very out of distribution when the task is not, or the situation is not solvable with test time compute or more thinking or more reasoning, then the safest thing is to stop and ask a human for help, for example. But this raises, like I think this makes kind of sense, but it raises an immediate question. How does a model actually know what it doesn't know? Because that's the whole adaptive reasoning framework from like the slide before. So scaling up compute when like the policy is uncertain, escalating when it's out of distribution, and so on, actually assumes that we have a reliable way to detect when the model is uncertain in the first place. And it turns out that's a very big assumption for our current machine learning models. And so this is fundamentally the problem of introspection. So knowing when a model does not know. And it remains really one of the central problems in machine learning. And arguably, it becomes even harder as we scale our models up. Because large models are often very good at pattern matching, pattern completion when while remaining poorly calibrated about their competence, because usually because they have seen like so much data, right? Genuinely novel situation can still appear superficially familiar. Making out of distribution detection very, very difficult. And in robotics, it kind of is even harder because failure can arise along so many different dimensions, right? It could be like objects, environments, embodiments, tasks, sensor noise, and so forth, right? And so like a policy can be overconfident or appear confident while being wrong for entirely the different reasons, right? This connects to another limitation on where the field stands today. As you have seen in the course, most of the current robot learning models rely on imitation learning. And as we saw earlier in the course, this means that the policy is bounded by the demonstrations in the data set. Now, think about like this kind of toy example, right? And how like this, what this means in practice. So for this toy example, this means that no matter how large your model is, if your training data consists only of demonstrations going from state 1 to 2 and from state 2 to 3, then the policy has no way of learning that there might be a better path, like going from 1 to 3, or that there might even be like a different way of solving a certain task that is not one that a human operator might demonstrate. So how do we break through this limitation? And as you have probably guessed, and also we have seen in the lecture before, one of the possible answers could be reinforcement learning, because as you've seen, the reinforcement learning is well suited to learn near optimal policies from suboptimal data by stitching together trajectories. So in this example, like for example with offline RL, it would actually be able to learn that like there exists a better trajectory that was not demonstrated in the data set. And we have seen how RL is really fueling a lot of new capabilities in other areas such as reasoning, agents, knowledge discovery, and so forth. But scaling reinforcement learning for real robots has been very, very challenging. And it still requires a lot of algorithmic innovation, so not just more compute. So I think really getting RL to work at scale for robotics is probably one of the highest impact things that you could work on right now. Now, figuring out RL for robotics might be also important to achieve, let's say, one of the holy grails of robot learning, which is the data flywheel. Like it is one of the kind of main goals of like the community. Probably you've already heard this before. The idea is pretty simple. So we know from the bidder lesson that more data usually translates to better models. And so better learning and models produce like more capable robots, and more capable robots get deployed more widely. And then, you know, with more deployments, we could generate even more training data. And then like this cycle like compounds itself, and you get like kind of like more data, better models, and so forth, right? So in order to get the flywheel spinning, kind of like the first idea that we could have is, okay, like we can co-train our models on both like the expert data, let's say like your teleop data that we have collected, and then the autonomous rollouts, so like the data that is being generated at the deployment, right? And then we can just like, we have more data, we train on this, beautiful, amazing. It turns out this is a more challenging problem than one might think from the outside or from the surface, because if you look at these two data distributions, they look very, very differently. So while the expert teleop data is kind of optimal, usually higher frequency, like smooth, autonomous rollouts will, you know, often be like quite longer in time. It will take longer to do the same task, often because maybe the policy doesn't always choose the optimal trajectory. It can also be jerky and suboptimal. And so if you like naively mix both of them, let's say with imitation learning, that will not work really well. The model will kind of get confused with by the mismatch in kind of the quality, frequency, and the kind of like just in general like the data distribution. And so this is another area where new algorithms are needed, because we need methods that can learn from all the data a robot experiences, no matter how good or bad it is, and kind of extract some useful signal from it. And this is, for example, an area where reinforcement learning could be well suited to help. But basically, the goal is really to try to never throw away data, because real-world data is like very precious and expensive. This is directly related to another broader open problem, which is lifelong learning, right? And so this means that, in a nutshell, a robot should improve over time by accumulating and learning from all the experience and interaction in the physical world, similar to how intelligent beings do. However, The dominant paradigm nowadays is that we train a model, we freeze its weights, we deploy it, and then ask it to generalize to novel situations that its pre-training data might not have prepared it for. And so, besides the mixing and learning from mixed quality deployment data, you also want to make sure once you start fine-tuning on this data that you don't have catastrophic forgetting, like forgetting about the model's original capabilities and so forth. And so this is a very exciting problem that will be very, very impactful. There is also a more immediate version of this. What do you do if your policy fails right now in the middle of deployment? Right? So instead of like retraining your model, you want your model to have the ability for rapid adaptation to recover on the fly. And imagine you unpack a robot at home for the first time, and you ask it to bring you a Coke from the fridge, right? And then maybe it tries and it struggles to grasp the handle of the fridge to open it. Maybe in that case, just giving it some language feedback might be enough, right? Like you can maybe tell the robot like, oh, like you just need to grasp a bit more to the left. That might suffice, right? So you put that kind of into the context of the model, and then it can like adapt and successfully finish the task. But maybe imagine it's more lost than that. Maybe it doesn't know how to open the fridge at all. So the easiest way might be for you to actually go there and do the demonstration yourself of opening the fridge, and then put that into the context of your robot's model. And so this is kind of like the vision for in-context learning for robotics. So this means instead of retraining your model every time it encounters something new, you want the model to have the ability for rapid adaptation by doing some sort of like few-shot learning from whatever signal is available. Now, if you remember a few slides ago, I said in order to improve generalization, robots need the ability to expose themselves to broader and more diverse data that they can learn from. And now, if we think about how mobile manipulation looks like nowadays, we see that it relies a lot on, let's say, the traditional SLAM stack to build like maps of the environment, localize themselves, plan the navigation, and so on. And then only once the robot needs to interact with an object, there is kind of like a hard switch to then like move to a learned policy like a VLA. And so there are several very interesting open research questions here where I think we will hopefully converge to a more principled approach that doesn't involve such a hard switch. So of course, first we would like to have like a more unified model that can do whole body control, so that it can handle both the navigation and the manipulation part together. And then second, there is a big question mark on what is the best way to represent the environment to allow for long-range navigation in a big building, for example. So do we need like an explicit 3D map of the environment, maybe a bird's eye view projection, maybe a topological map is enough, or scene graphs, or maybe just someone walking through the office like a walkthrough video with their iPhone, and then just put that kind of video into the context of the model. Maybe that's enough. And how will such a model, like such a unified model, then handle state estimation? Like, will it be like implicit? Will it be explicit? And if we put some sort of environment representation into our model's context, how do we handle environment changes, right? Because like the environment is not static; it like continually like changes. We probably also want to be able to have some ability to adapt to some sort of like local navigation without a map. So these are all very exciting open questions that I think are really fantastic to explore right now. And Maybe the last one, if we have such mobile robots interacting with the environment over prolonged periods of time, then they should also, of course, be able to do this sort of lifelong continual learning. And if you think about this, we stumble across another very interesting question, which is about memory at scale, right? Because like a robot generates a continuous streams of multimodal experiences, like video, depth, language, touch, audio, bounding boxes, etc. All of this is potentially useful, but the question is like, what do you store and at what time scale, right? This can range from short horizon memory, such as very dense videos, to longer horizon memory, where you probably want to try compressing experience into like more semantic events that maybe like helps you also remember what you already have done and for like task progress and so on. But like then you have to kind of think about when to write to memory and what to forget, which is also kind of an interesting question. And then you can think about this all the way to years, right? Like how do you like store all of this? How can you retrieve? How can you do like cross-modal alignment and so forth? So these are all interesting questions, and I can share some initial work we have done towards addressing some of these. So VL Maps fuses VLM embeddings into 3D spatial maps, enabling zero-shot spatial navigation to open vocabulary targets without any training whatsoever, so it's really out of the box. Or Lilan is kind of like learns how to do mapless navigation entirely from videos, like YouTube videos. And like we showed that the more YouTube data we train on, the better the performance gets for open vocabulary mapless navigation. We also have some preliminary results on how to use foundation models to enable autonomous improvement without human interventions. For example, by proposing and scoring tasks based on environment affordances. And regarding adaptation, also a few, for example, on the left, Palo is a non-parametric approach that allows generalist policies to adapt to new long horizon tasks with as little as 5 demonstrations, while achieving the same performance that full fine-tuning would achieve for the same model with around 100 demonstrations, if I remember correctly. And so in order to achieve this kind of embodied intelligence, I think a lot of the problems I just mentioned can be distilled into these pillars of embodied reasoning, dexterous mobile manipulation, lifelong learning, and rapid adaptation. And so these are the things that I think that will actually will need it to be solved to make robotics work, like not just like for like a demo video, but like in general. So maybe this is my end game for robotics. All right. So I hope that after this course, you all have a better understanding about like the tools that are available in the modern robot learning researchers toolkit, and that if some of these problems excite you, you can start advancing the frontier yourself. But knowing what the open problems are is only like half the battle. The other half is knowing how to do actually research in robot learning or in general, research in general. Before finishing, I would like to share a few things that I have learned about how to do research, sometimes the hard way, that I think might be useful also for you. So to start with, some uncomfortable facts of research. First, most of the research is incremental, and that's not like a criticism. That's usually how science works. an analogy, for example, like today's self-driving cars, like rest on around 40 years of like research and accumulated work, right? From like the Alvin car in 1986 to the DARPA challenge to end-to-end modern learning. Like nobody solved it in a single paper, right? Second thing, most research ideas never become papers. So you might have like 10 ideas, maybe you run like 5 experiments and get 2 interesting results, and then maybe you publish 1 paper. And that would be like a good ratio, I think. But like the fact is that most of the ideas you have like usually don't work, right? And that's like not like a failure, but that's kind of the process how it goes. And also the third point is that most of the papers don't stand the test of time. So the field moves really fast, and you know, something that might feel like a breakthrough today might be considered like a footnote in 2 years, right? And the fourth point I want to make is that so in a world where scale is important, simple ideas tend to have more impact because they can be scaled more easily. So this means that if your idea requires 17 different moving parts to work, then maybe try to ask yourself if there is a simpler version that gets you 80% of the way there. So how do you find a good research problem? What is like a good recipe for this? I think it's simple, and I will briefly go over it. First, you need like an important problem, and then second, you need a plan for how to tackle it. You need like both, like the problem and the plan. Just having one of the two doesn't get you all the way there, right? Like an example, like you could say, you know, let's cure cancer. Like that's a really important problem, right? Sounds very impactful. But in this case, if you don't know how, then you know maybe it's not the best idea to start working on that, right? Conversely, let's say you have a new algorithm that improves 1% on the Libero benchmark, which is a very narrow and saturated simulated robot benchmark that does not really like move the needle on anything that matters. So the sweet spot is to try to think of like a problem that is important and where you have like some angle of attack or like some plan on like how you want to like address this. And then maybe the last point here is also good to think about, you know, if your plan works exactly as you have thought and you are like successful, how will this look like? What will it like unlock? How does it help the community? Like, will something be now possible that wasn't possible before? These are good things to think about. The next ingredient you need, and honestly, probably the most important one, is excitement. Because a research takes a lot of time and effort, and you know, experiments don't work, there are deadlines, sometimes paper rejections, and so, you know, it can be painful sometimes. And what will probably make you more likely to succeed is if you're also excited about the problem. Because if you kind of like find the problem interesting and exciting, then the hard parts of getting there like feel worth it, if that makes sense. And if you're not excited, then it just feels like work. All right. There's a fourth ingredient that I think is also quite crucial for making being successful in research. And you know, hopefully you attack some of the problems we just mentioned before. And this is trying to be your own reviewer number 2. So, you know, when like you submit like a paper to a conference, you know, this is the reviewer that's like very critical of your work, right? And so what I mean by this is that before you go on and embark in a long, like, multi-month like research journey for a particular problem, you should try to ask yourselves, what is the most likely reason that your idea might fail, right? And now, if you can answer that honestly, and you still believe that the idea is worth pursuing, then you're good. Then go ahead and proceed. And why I'm saying you should try to do this is because this is a tool or basically a way you have to protect your most valuable resource, which is your time, right? In general, there are two different styles of research, and it's worth knowing which one you're approaching. There is the method-driven research, which starts usually with an idea or a technique, and then you kind of need to find the right problem for it in order to have an impact. Today, it could be something like, a new video diffusion model just was released. Let me try to apply it for robot manipulation. Somehow, like, I don't really know, like, what exactly, what problem or how, but like, it's like a kind of like a cool new shiny model. I want to like use it for something. Problem-driven research starts the other way around. Like, you start with a concrete problem. Let's say, for example, how can I make a VLA generalized to a novel camera viewpoint? And then you go and find or invent, a method that solves it. And so the problem is kind of your anchor, and your method is like whatever like solves your problem best. Both styles can produce great research. For a PhD, I probably would recommend problem-driven is safer, because if the method doesn't pan out, then you can try another one, and you will still be trying to solve an impactful problem. But if you never had like a impactful, like a real problem to begin with, if your method fails in the method-driven research approach, then you don't have anything to fall back on. Okay, but how do we actually do research? Here are some loose tips. I always recommend starting with something that you know that should absolutely work, and then go make it incrementally harder. Right, so maybe start with some overfitting experiment before you try solving all the problems at once. And also always make sure to visualize both your inputs and outputs to your models. It's really, really important. Because if you start out at full complexity and your experiment fails, then you have no idea what the problem is. So you need to know which parts work incrementally in order to push the boundary. And I also recommend always talking to people about your idea, colleagues or authors of papers you're building upon. This can really save you weeks of effort or work. And once you have results, share them. So share your findings with the community. The people who care about the same problems as you do might be like your next collaborators, for example. Try open sourcing your data, your code as much as possible. This is the most direct way for your research to be useful for others other than yourself. And also try to invest some time in polishing your figures. Ideally, someone should be able to look at your figures and immediately understand what's going on without like reading the whole paper or captions. If they have to make an effort to understand your figures, then they will move on and not bother like reading like your paper or your blog or whatever. And when sharing your research, be mindful of your audience. So in doubt, don't assume that your audience already knows all the same foundations as you do. And of course, one more thing on sharing, if nobody knows about your research, then it basically didn't happen. So a great paper that nobody has read has like zero impact. So like try to disseminate your findings, put your work on archive, post about it on social media, etc. But remember, like I think this brings us kind of to the beginning of today's talk. Try to find the line between like making people curious about your work and not overhyping it by saying you have solved robotics, or like in Brett Adcock's case, where 2 years later after the tweet, we are still waiting for his ChatGPT moment in robotics, right? I want to end today with a personal story that I think maybe illustrates a little bit some of the things that I just try to give you some suggestions on how to do like research, how to tackle them. So early in my PhD, I was kind of drowning in the classic robotics pipeline. I had 1,000 ROS nodes, disjoint models for perception, planning, and control that were accumulating errors across all this super complex pipeline. Not only that, like a week before a major deadline, the robot broke. It wouldn't finish self-calibrating at startup, so it wouldn't allow me to run any of my code. It was a bad time. And as any good computer scientist, like any decent computer scientist that that would ask you in such a situation, what do you do? Like you try turning it off and on again, right? So that's what I did for actually a few days until it somehow finished self-calibrating, like I think the night of the deadline or something. And then I had to pull an all-nighter to run all my experiments for the deadline. And so this very traumatizing experience turned into a bigger question for me. Can I ditch all of this? Can I forget about all this ROS nodes, all this super complex pipeline with 1,000 models, and just accumulating all the errors, and do end-to-end learning? So really, because of this experience, I asked myself, what would it take to have a cool end of PhD demo where instead of all these ROS nodes, I have one model that can do multiple manipulation tasks, end-to-end, and that can be commanded and instructed with language. And so I wrote actually a proposal with some very loose ideas that got accepted and funded me for a few years. I then convinced my PhD advisor to buy me a Franka robot. I'm very grateful for his help with this. And then I went on and spent 1 year setting this robot up from zero with custom heavy, a metal table with holes. Writing the VR teleop code, mounting cameras, 3D printing the mounts for the wrist camera, figuring out how to make the low-level controller smooth and whatnot. All of this was a lot of work. So I spent a year on this. And then once I had a working setup, I started doing a bit more research. Once I started doing research with it, I quickly realized that iterating in the real world would take me forever, and that I wanted to graduate at some point. So I started working on a simulation environment that used basically the same stack for teleop, as you can see on the left video, with the VR controller and so forth. And after spending some time on making the simulation nice, I realized that actually there wasn't any simulation benchmark or data set that allowed training these long horizon language condition policies that required some degree of generalization. So I thought well, maybe I can try to polish a bit my sim, and maybe I'll make a small paper out of it or something in case it's useful for others. And so this kind of byproduct or even afterthought that I had become then the Calvin benchmark, which to this day is still one of my highest cited papers and also won a Best Award. And building all this infra to set up visual motor control policies was hard work, especially in a lab that primarily was focused on doing SLAM. But then this allowed me to iterate very quickly on the problem that I actually wanted to solve. And it took me about 5 years with this setup to get to my cool end of PhD demo that wasn't running any ROS and could do over 25 different manipulation tasks, all grounded in language and generalized, to unseen combinations of them and so forth. So I was very happy. Okay, we are at time. So this was my last lecture of the course, because next week we will have guest speakers only. And so I wanted to take a brief moment to say thank you for all your patience, because this being a new course, it has taken a lot of effort to put together. It really felt like we have been flying a plane while building it at the same time. And also a lot of thanks for like the feedback you gave like on the midterm. That was really useful and hopefully made the course better. This was the first time I have teach a full course, and the first one where I had to like also design from scratch all the materials. And so, although juggling also 2 full-time jobs at the same time, because I'm not a professor, I work at industry, I can say that teaching this course has been an absolute privilege for me. And like seeing the students excited about how their policies are training, like scheming, like to share data across different teams, or asking our guest speakers insightful questions, I think that makes me like really, really happy. And the goal of this course is really beyond teaching you like the content and the basics, really to inspire you that robot learning is a cool field to work on. And I hope that we were able to convey this. And with this, I'm really looking forward to seeing all your projects with the real robots on the demo day. I think that's going to be a lot of fun. I can't wait for it. And before we finish, and I pass on to Lucas, who hopefully is somewhere here, there is one more group I want to thank. I want to acknowledge the teaching assistants, because like this really would have not been possible without them. So designing a new course from scratch while working 2 full-time jobs is hard, but the exercises, the project supervision, the robot setups, the TA session, that was all of them. So I would ask the TAs to stand up. Please stand up and let's give them a big applause. Awesome. And with this, we are done.